smart home hub, and into Nifi, we created a Python script that it was effectively a SSE client. So we could receive push notifications to this Python script and then feed them into Nifi. We also set up Nifi on EC2, right? Because we wanted to transfer the data out of the home or the edge, so to speak, and up into the cloud and be able to reconsume it in other areas and do our analytics either up in the cloud or technically in a data center, cough, cough, my basement. And then we did have a little EC2 Hadoop cluster. We used my bare metal stuff, and we used Pig and Spark for the analysis of the data, right?
So the Spark aspect is we bought all the data to Spark, but we're not data scientists by trade. We enabled analysis, we enabled analytics, we got the data there in a good state to start the exploration. We're not the right team to necessarily present novel types of analytics, but what we do is get it there so the right people can start to explore it.
Exactly. We're not domain experts in the home, even though we live there. So architecturally, right, we went with a hub and spoke approach. It's fairly common. The hub you could imagine, in this case, being where you're going to store all that data, where it finally lands and aggregates to, right? So that would be the Hadoop cluster in my basement or in your data center, right? Potentially, it could be, you might have multiple hubs depending on geo reasons and other legalities. So we save all of the historical data in there, and the entire goal was to prep the data so that it would be usable then in Spark for all of our various analysis. The spokes in this case, right, are actually cloud deployments that the edges push to. And so this gives us the ability to have kind of per region, per geo capability, both from a legal standpoint and potentially a latency standpoint. The real-time streaming data gives us the ability, right, to have up in the cloud something that is, how shall I call it, near real-time. It's not exactly real-time because real-time, in my opinion, requires you to actually be on the edge, right? That's the only place you'll make those decisions fast enough. But for a large majority of applications and use cases that we could think through, having near real-time, under 10-second responses to anomaly detections and stuff was more than acceptable. And then the other thing that spokes kind of provide you when you get back to that legal geo kind of need, if you were in here for the last presentation, they were talking about having to cleanse GPS data, right, out of China before they could send it over the pond, because those are elements that we can't send. So the spoke architecture being deployed per geo gives you that capability to redact any elements that you need to in that local geo and then transfer what was acceptable to leave that geo back to your hub.
So let's talk about how this actually all comes together now that we've done the high-level overview of what we're hoping to accomplish. We have a lot of sensors. These sensors might know how to connect to a wireless device, but they don't necessarily have internet protocols on them. So we have all these door sensors, all these window sensors, all these motion sensors. They're all going to go through a centralized hub in order to get off-site. That way, as we need to control the data access policy, I don't need to worry about all my doors communicating with these hackers that might be trying to get in the future. All I have to do is worry about this Raspberry Pi and other gateway devices and how they're communicating off. So then we went through a few iterations on what the cloud is. At first, we were actually doing it straight to the data center. But that led to a huge problem where a few servers in a basement isn't very reliable, and when it crashed, we'd actually lose all our data just because everything would crash and because it's a basement data center, literally. So we decided to use the cloud, which is a naturally reliable, resilient platform. All the data would land there and get stored there, backed up there. And then if we wanted to ship it off to a basement data center where water might be leaking in, we could do that. But the point is we get reliable transmission off-site to a secured environment, which can run our Hadoop platform for exploration and our data cleansing. And then from there, we actually are able to ship it to multiple sites. So Nifi has the ability to send it to multiple different recipients with different filtering options. So I was able to filter data, send it to my, I was actually running a sandbox at one point. So let's just say I was able to filter out a small amount of data, send it to my sandbox. Or we can initiate a full, just pass all the data through to the unreliable data center that maybe we're losing a connection with.
So beyond that, there's some really key things in this design. First off, you're not seeing any of the bidirectional stuff. We'll talk about that on the next slide. Okay. What we really wanted to emphasize in this slide is that you can have an edge that does not need to receive a command, right? As long as you can architect it in such a way that either it will continuously pull or push data out, right? And that gives you the ability to run that behind a firewall, or in the case of the home, you're going to have a router and it's going to have like a 22 SIDAR on it, and you won't resolve the actual IP address of that Raspberry Pi running Nifi inside of the home, right? So we got rid of having to understand mappings, port forwarding, all of that stuff by architecting this in a way that the edge is either pushing or it's pulling its own updates. So it originates all of the connections. Nothing comes to it.
From the privacy perspective, this is colossal. This just means your smart home can communicate out to the hub, and the people in the cloud, the data scientists in the center, can't ever reach back into your home. It's securely one-directional only.
Yep. And the same thing kind of applies here for the data center, right? The data center is architected in such a way that you don't have to expose a public endpoint to it, right? Your public endpoints are all in the cloud. You go to the cloud if you want the public to touch it, and then you ship stuff back out of the cloud. So we did a majority of the push and pull lines in here utilizing Nifi site-to-site capabilities. Site-to-site capability is very interesting because it has delivery guarantees. It can compress the data, right? So when you're looking at the line from the cloud going back into the data center, you're going to pay egress, right? You want to pay less egress. So compress the data before it gets shipped out. The data center Nifi also could be, if you couldn't get through the firewall, has native HTTP proxy capabilities now. So you could actually route that traffic through an HTTP proxy if you weren't able to resolve the DNS appropriately to your cloud endpoints from inside your data center. So bidirectional communication. This there's lots of options to this, right? And I wanted to kind of talk about it from the different perspectives. So you've got the edge to the cloud, right? So this is literally the collection of data. How do you push that using site to site for receiving, right? Or you could pull updates utilizing just simple HTTP, right? So Nifi has an HTTP processor that you could link up with the distributed cache and populate rules in there where the smart home hub knows its identifier, right? And it makes an HTTP call up to the Nifi or cloud that's running and receives the latest update as a JSON payload back for how it needs to change its own algorithms that it's running. Okay. From the cloud perspective, right, I already mentioned kind of the distributed cache. So that gives you a place to centrally store rules still within Nifi. Right? And then obviously, right, the HTTP processor, and then finally site-to-site capabilities for both pushing into it and pulling out of it. And then finally, the data center to the cloud. So I thought this was slightly more interesting. Obviously, you know, we're pulling, right, from the original diagram, but then if you want to start thinking about how am I going to do bulk updates and push those back into the cloud, right, there's obviously numerous options. One of them could be you just hit all of the HTTP processors and create an update flow. I thought that was a little bit crude, honestly. I think a more realistic flow is going to be people running analytics inside the data center, outputting a file of brand new rules, right, and then utilizing, say, Nifi's pull from HDFS and site to send a whole blob of rules to a specific pipeline inside of Nifi to update that distributed cache. So the home collector, and we're just going to give a very high-level overview of my home collector because it's changed many times and it's a little bit crude.
This is the device that collects the data from the door sensors. This serves as the gateway rather than the home sensors trying to send straight to the cloud.
Yep. So in this one, right, we've got my Python collector where it says collection, and then we're also collecting all of my router logs using syslog. This is how we found out that my house is getting pinged pretty much every minute from various countries. Was it?
Portugal and China.
There you go. So we played around with that, and then something else that I had kind of came up with that we put into monitoring that we won't dive too deeply into, but have you ever wondered if your internet connection's actually up all the time? Yeah. So I built a unit that goes and fetches from multiple different websites the page and monitors for lack of activity, and then monitors how long that lack of activity lasts. Okay? AT&T is not going to like you when you tell them that you want to refund prorate because they were only up 97% of the time, even though you weren't using it at 2 a.m. The redaction stuff, so we'd kind of mentioned some of the capabilities as far as Nifi goes to remove things in a particular geo and move it all around. There's one key thing on this slide. I'm wondering if anybody in here actually knows what it is. You see the little funnels that are kind of on there? That might be hard to see. They're white. Okay. Does anybody know why you would not want to just push stuff into a funnel? Okay. So these funnels, in the way that they're configured, right, will hold that data forever. It's just kind of an endless bucket. That's not a good pattern to implement because it's not purging automatically for any reason. Okay? It's just going to fill up the Raspberry Pi's disk, and sooner or later you crash. And we know, because that's what happened. Now, the legitimate use for funnels here could be in QA validation. Right? You want to validate how many messages went through, and you need to collect all of the specific type of message in a given bucket before you can analyze it and make sure that all your appropriate counts went.
So the important lesson about the funnels and stuff is as we move from batch to streaming architecture, we really need to think about how sustainable something is. So if we have a few dead letters that appear in a batch process of unprocessable messages, that's great if it runs once. But if it's running 24/7, that bucket's going to get bigger and bigger unless we think about it and plan around it. So this is the first generation of what we put in the cloud. This is what was receiving the messages from Joe's house and starting to decrypt them and store them in different places.
I want to put all this into context of what you guys are about to see. Right? Nifi, with its GUI, is exceptionally easy to use. It's also exceptionally easy to put yourself into the corner with because you're not thinking through necessarily what you're designing because you're rapidly iterating through it.
So this is the first generation design. This was us thinking, OK, we need something that works. Let's just see what happens. So we received the messages, and first thing first, we decrypt them. The connection wasn't actually secure. We decrypt the content, which was encrypted. And then we're going to write it to local disk. Then we thought, OK, it's on local disk. Now what do we want to do? Well, let's store it to S3. So we take it from the location on the local disk, move it to another directory, and during the move, we copy it to S3. And then we said, well, I don't want to interrupt my S3 process, but I also want it to go to RDS now. So now we take it from the S3 directory and put it in another directory while copying it to RDS. This was a great first-generation architecture because no matter how many times I messed up my RDS connection, I never broke my S3 connection. But if the S3 connection ever broke, guess what? I'm not getting it into RDS anymore. So that's a problem where any failure at the disk, S3 or to RDS, could potentially just stop the whole process. Plus, RDS is going to have relatively high latency because now we're waiting for S3 to complete its upload before we start posting to RDS. So second generation, as I'll show in a minute, is how do we fix that?
It's also worth noting here that when we wrote directly to disk, we actually lost out on certain Nifi features that would have purged data that was, say, the oldest data, depending upon the rules that you've set up. By writing it to disk, now it wasn't being monitored anymore, and we could just fill those disks up automatically. So we would rather have a system that continues to run, even if it loses a certain amount of connectivity and has to start losing certain events. So the decryption side of this was basically me saying that I didn't want to set up SSL certificates, right? Let's be honest. I really didn't want to go through and generate a bunch of SSL certificates. So what I did,
which is typical, because your average homeowner won't have his personal SSL certificates in line, as I've experienced.
So what we did here was for all of the streams that I transferred out of the Nifi in my home, before any data would be moved, we encrypted it with different AES keys. Okay, so we just said the entire payload's encrypted, therefore I do not care that the channel is not encrypted at this point.
So here we're decrypting the home event stream, which is the sensor data, and the wireless router logs separately. We never merged those streams in generation 1 because they had to be processed differently. This means we have insane amounts of overhead because now we're managing 2 pipelines instead of just one intelligently built pipeline. And that really started to rear its ugly head in this step, which is where we're writing to disk. The router logs are being merged into one large file, about 100 megabytes, and being written to disk. But since we didn't really feel like doing that for the home events, which weren't nearly as populous, those are just writing straight to disk. So now we have 2 separate policies in our Nifi writing to disk separately. It was very easy to implement because I could do one, then the other. I could mess one up and it won't mess up the other. But this really started to be a pain in the neck to manage 2 separate streams as the idea emerged. And I'll show you guys how we were able to move it into a common architecture.
This is also the example of how easy it is to hurt yourself in Nifi. He just said that, right, for all the home events, because the frequency was so low, we just wrote them one at a time to the disk as its own file, right? Everybody knows the small file problem on HDFS, right? So it's exactly what happened next as soon as we tried to load those onto the platform was we had 87,000 small files, and it created numerous other issues.
So this is where we started to say, this is not cool. We need to start getting our stuff together and be a little more professional if we're actually going to present at Summit. So we thought the first step should be everything should write together. So here what we have is the same workflow, but instead of one feeding the next, it goes to all of them at once. So at the top, so you could see with the queues. So Nifi has the cool ability to have different channels and process messages separately. What you can see here is we write to S3, to disk, and RTS all simultaneously. So if RDS was to fail, it would not trigger a failure in S3. If S3 was to have high latency, it wouldn't increase our latency to RDS. This is just 3 separate data stores, but if you think about that as different business units in your enterprise, if marketing messes up their data stream, it's not going to knock manufacturing offline just because they decided to stop accepting connections. And that's how this starts to really get powerful. But the thing here, if you notice, is in the middle. We have 2 connections going between decrypt and to disk. We're still managing separate pipelines for different events in this. So despite writing all of our events to different sources separately, the pipelines are still separated. And then the 3rd generation is when we decided to fix that too. This shows us adding tags. Nifi has a separate metadata store for all incoming information. This is separate from the payload data. This means I could change the metadata in Nifi without even risking altering the data payload itself.
It's called a flow file. So in Nifi, you have a concept of a flow file. The flow file has a payload, and it also has various attributes that you can assign to it, and they can be any type of attribute that you want to assign. So when we say add tag, adding an attribute to a flow file.
So this now, the moment this data is received, we tag it as a home event or a system log, and then we say, now we're just going to pour all of these in together. Think of it as just dumping it all in the same bucket. They're colored balls now. We could sort them out later if we need to, but who cares for a lot of this? They're with the same decryption key. Let's pump them into the same decryption processor for now. And then this enables things like this. This is now our write-to-disk process. If you notice, multiple types of events are all coming in on the same channel. The merge content processor, which will take all the small events and make them into a large file, can only merge unlike tags. So no longer do I need to worry about different funnels with different rules all writing to disk. Nifi can, even within the same pipeline, apply selective rules and selective merges and write it to disk. And the to-disk processor has the ability to accept variables. So not only are we using one pipeline, it's still writing to separate directories due to our implementation of variables. So then now, no longer do we have to worry about, OK, this processor writes this type of file. It's all the same. This makes it very easy to maintain in the long run.
And then the split flow, right? So this is basically getting back to his analogy of the colored balls, right? So we've pumped everything into effectively possibly one of the same bins, and now you can route back out based on the attribute that is on that ball, or ergo the color, right? And send it down separate paths. In this one, I can't even read it.
So in this one, we're handling the two disks slightly separately. In this case, the directories needed to be set. In this case, there's still an architectural issue of where the directory name is not the same as the tag. So we decided to update the path slightly separately. So what you're seeing here is a split based on the tag, or the color of the ball, and then a different directory before it goes to disk being applied with different rule sets, before being re-merged into the same write.
So we definitely figured out my wife could not stand this. And it got really bad when we could tell her, hey, you left the door unlocked, or you left the window open when you left the house, right? Because when you start looking at it in conjunction with your router logs, all of a sudden you can see what smart homes are actually at home, right? Or smartphones are at home, and that gives you the capability to start identifying who's actually an occupant currently and who isn't.
So I learned firsthand of the importance of scrubbing data from this. So when we were able to send a text automatically that your cell phone disconnected from the Wi-Fi and we have a door open without a door close activation, go home and lock the door before heading out, she was not happy. But so we started scrubbing the data a little bit more and introducing privacy protections to prevent that.
Other interesting things we found, right, is obviously the radius of your router, and for your phone to be able to join it would let me know that my wife had actually just started to pull down the street before she got into the driveway, because I would get the ping from her MAC address on my Wi-Fi router, right? So now I start knowing that, hey, she's about to be right here. I better go open the door so that I don't get yelled at for not bringing groceries in or something.
We also have learned that dogs and humans appear very similar on motion sensors. But dogs, fortunately, don't often carry cell phones. So you can often tell that the difference between a human and a dog in the room based on the presence of their cell phone if you have multiple Wi-Fi hotspots.
Yep. And that kind of leads to the fact that motion alone we felt was almost useless, right? We really had to use it combined with something else, such as the smartphone joining or leaving the network, or various door things happening to decide if it was actually somebody leaving, somebody entering, so on.
And a future use case, a few that we have in mind is, in my experience at least, sometimes the delivery people will say they came when they really didn't, and now we know for a fact whether or not the truck pulled by because it has a unique signature. We also know whether or not we have to remember to let the dogs out in the morning, because the back door needs an activation before the front door leaves and your cell phone disconnects.
Yep.
So you have to really start thinking about the patterns that'll start emerging and what we need to look for and where we can get different information from. So from the insurance perspective, if this person leaves their door open constantly, that might be an issue, especially in Detroit.
Yeah. Speaking of my dogs, right, we actually figured out, based on all the door open and closes, that my dogs try to go out every 47 minutes, right? Not on the hour. Always about 47 minutes they're asking to go back outside. So, yeah. All right, so challenges, right? This first bullet here about Oracle versus OpenJDK is specific to the Raspberry Pi or anything running an ARM processor. Do not use OpenJDK if you are running on an ARM architecture. Nifi took about 25 minutes to start, okay, using OpenJDK. As soon as we switched it over to Oracle, it took 1 minute. And it was done, and everything was significantly better. It's
important to note that this advice only applies to what is going to be running on an ARM architecture, not necessarily your day-to-day servers.
Yep. The other thing we ran into very quickly on the Raspberry Pi was if I had lost connection to the cloud and I had to start aggregating data and waiting for that connection to be restored, kind of like a jagged edge, I would fill my flashcards, right? And then it falls over and you stop collecting data anymore. So the fix for that is Nifi has the capability and the queues to configure back pressure, right? So you can come up with those rules for purge the oldest event first, or start purging events as soon as we've collected more than 10 megs in size.
So when we first started this project, actually, that was a huge issue, because before the cloud, just when we were starting, we decided that a sandbox with Nifi pre-installed would be a great endpoint. Unfortunately for my day-to-day job, I often have to run different sandboxes, which would mean Joe's connections go down. Joe texts me, why can't he send out his data? I don't respond because I'm presenting a different sandbox right now. And then the entire home crashes because we didn't configure back pressure properly. So stuff like that is why we really started going towards the cloud. But the lesson is still there, is even if it's not somebody's sandbox, if it's an unreliable connection in a certain part of the country, you need to configure your back pressure so your system doesn't fail. Nifi has the ability to say, let's stop accepting new messages, or let's start dumping old messages. And if we think about that up front, we could really start understanding the failure characteristics of a system, which is something that is often an afterthought instead of the forethought.
Yep. Flow file names need to be unique when you merge them. Okay? So if you're generating flow files or records and the name is by timestamp, and you generate a whole bunch of them in the same second, and they all come out with the same name, it's not going to merge them properly, and you're going to have a bad time.
So a little bit of background here for those of you a little unfamiliar with Nifi. Whenever a data parcel is received, it becomes a flow file, which basically means metadata gets attached to it, and it gives it a unique ID. We, in our infinite wisdom, decided to overwrite that unique ID with something that wasn't unique, and it led to all the problems you just said.
Yep. Site-to-site configuration. So if you're doing site-to-site transfers and you have an edge device inside of a LAN, right, the IP address for that configure is the WAN IP address. Okay.
This also led to some goodness where, since I couldn't reach back down into the house, Joe's wife could theoretically turn off the transmission, and I could not think, oh, we're not getting data, I better go turn it back on, and just further inflame those problems that were occurring earlier.
So the Python SSE push collector that I had mentioned at the very beginning, while easy and worked for a POC, turned out to be an absolutely horrible idea, because to execute that in the Nifi context, there's something called execute process. Simple, okay? This is like crack for Nifi, right? Everybody starts using it, and then it has problem after problem after problem. If your script that it's executing is not perfect, in the sense of how it handles its failures and stuff and doesn't gracefully exit on an issue, the site-to-site processor will believe that it's still running, and you will get nothing.
So the merging large files is really relevant to Spark. So let's talk about Spark and how this data could actually be accessed. At this stage, we have the data in RDS, which is functionally MySQL. And we also have it in small files. So if we want to build a data frame, we can either query it, or we can load the small files. Well, like most Hadoop, Spark doesn't like small files. So this really became an issue where we couldn't load the data into Spark. We said we're going to get the data ready to load into Spark. It doesn't load in Spark. The project's a complete failure unless we fix this, because we failed the primary goal. So you need to think that you need to be ready with the data scientists in mind, because that's the end goal of this. Honestly, the whole project would have been a failure. We ended up going back and putting the merge processing units in earlier to make sure only big files got written down. And we also used Pig, which can be overlooked with all the Spark popularity nowadays. Pig is still a phenomenal utility for cleaning up huge amounts of data, particularly if you had someone who didn't think about what they're doing when they wrote it, such as us. So once it was in big data sets, once it was all there, all of this very cleanly loads into Spark. So if we have IT ops guys here, just get it into our, MySQL or a SQL Server or RDS, get it into big files, and the rest really just starts building itself, which is why we haven't put too much time into it, just because it literally just loads into Spark.
And then, from a challenge perspective, I had mentioned I would not buy the same smart home hub again. So definitely do your research if you decide that you want to try and integrate with one of these. Make sure that the hub you buy doesn't have to send the data to the cloud to receive it again, to push it to your device.
So this has to do with the architecture here, where functionally we're getting the data from the devices, but some devices, for some reason, probably DRM reasons, need a connection to their home server before they transmit out. That just is completely opposite of all the architecture we're trying to implement. So pay attention to the devices that we're using. Think about the connections they all need. We just got done saying the smart home devices don't need to connect to the internet. That's the ideal scenario. However, some manufacturers feel the need that they do need to connect no matter what. So just keep that in mind if you're developing a building level infrastructure. I've been seeing a few hands here and there. Over there, I thought I saw one. Nope.
So after this, we're also all going to the Hortonworks, the community connection corner, so you can hound us over there as well. Back?
Yep.
Sorry.
Can you speak up a little, please?
Are the details for this documented online in case I want to access?
So the question is this documented? I believe this presentation is being recorded and will be shared. However, most things we've done are covered in the new lab series that our Hortonworks team has put out. And we're actually going to discuss that at the, if you come by the community area later.
Come up here, man. You asked the first question.
Yes.
You.
Yeah.
So you mentioned about merging the content. So what were the parameters by which you are merging? Number of files that you're taking in, or
So the question is, what parameters do we decide to merge the content on? And this is actually, once again, where we have to talk about with the data scientists and Spark and thinking about what do they want to use. So we knew smart home events would potentially be separate than router log events. So with our domain knowledge, we were able to say this type of data needs to be lumped together while this type of data needs to be lumped together. So we were using a data type label to collect. Right. So Joe, do you have some guidance about how to size good Hadoop-sized files?
I like to say that it should be at least one block, which is 128 meg.
yeah. So the question is more on what monitoring do you had on your own as you're aggregating the data. Yeah, it's ideal to have it on a block.
So this isn't production. We didn't really set up any monitoring.
Okay, additional questions.
So, any ideas of adding video monitoring and streaming?
So
We're talking about your dogs, and in and out of doors is very nice, but
yeah.
I have 3 dogs myself, so doing other things. So.
Yeah, so actually what I wanted to do was set up a webcam and use something like Python OpenCV and build a mailman detector because I have the same mailman typically, so I could do a facial recognition against him to determine that he had actually came by my door.
So,
But my wife is very anti-real camera now.
so to go into some management consulting with my 3 minutes left, if the partner's wife is relatively unhappy with the solution, it's probably a big reason not to go forward with video monitoring. There's a question all the way in the back. So Spark Streaming is made to analyze a lot of data. It's made to do the machine learning on it. Nifi is a light touch routing engine. If you noticed, at no point did Nifi make a decision for us. That was all those insights we gained was through our Spark exploration. So Nifi got the data there. Spark enabled us to explore it.
The other side of that, right, from a Spark Streaming perspective, is that Spark Streaming is going to be micro-batching things up, right? The Nifi instance allows us to say, crap, we couldn't connect to the endpoint that I need to transfer the data to for the last 7 days and hold on to it all still and then move it all at once. So it's all about data pipelines and data movement. It comes with it. It's out of the box. Nifi is the easiest Apache project I have ever had to install. Go to their website, click download, download the tar, untar it, go to bin, run sh, start Nifi sh, and it's done.
It's also included in the sandbox nowadays if you add it as a service.
You guys have shown the flow from data flow from Raspberry Pi to the cloud. What's the flow for if the user have to send the instruction back to the sensors and the devices?
So we had talked about a little bit of the bi-directional communication stuff. And again, it's really all about how long are you willing to wait from a latency perspective, right? So I can have my edge device at the home continuously refresh every 5 seconds and hit that cloud endpoint to see if there's been a new message delivered from my phone, right? This is all about user experience and what you decide is acceptable for latency.
So from the theoretical perspective, Nifi has the capability to act as a fully functional REST server. So as the data is getting posted up, we can give it a code saying, make a post here and pull down the data.
How it's different from the Kafka?
Well, let's talk about that offline.
Yeah, just come up after.
Is Nifi
One more.
recommended for data
Okay.
transformation, or is it for data transformation, or is it purely
Light-
for delivery?
Nifi is great for light data transformation and light analysis. If we needed to do some heavy transformations where we're computing things, we might want to start looking at other streaming platforms. But if it's receive the data, do a lookup or two, refactor it, and then post it out to Spark Streaming, Nifi is the ideal and most usable platform.
Last question.
Why do you move data from the cloud back to the data center?
So from a cloud perspective, right, cloud storage is expensive, especially in terms if you're looking at purchasing your own hardware. The data center costs, as far as terabytes go, you're looking at pennies per gig potentially. That may not seem like a massive difference, but we find it to be. You'll also potentially have more compute in your data center, right? You'll have a lot bigger muscles for analytics to happen in your data center compared to being up in your cloud, where I don't want to pay that much per day to be able to let my data scientists go run jobs up in the cloud. I'll do a big CapEx investment and put a Hadoop cluster in my data center, and I'll keep my OpEx as low as possible and only size it to what I need to be able to service my customers.
Also, there's an organizational advantage. Here we didn't show it being combined with any data sets, but let's say I get very sensitive data in my data center and I need to combine it with home events. By pulling the data into the data center, that sensitive data never has to leave the data center. So that's the type of work we could start enabling with it. We could also push the home data to a country that doesn't allow the export. So if we're working with China and we can't export GPS data, then we push it to the Chinese data center and we can suddenly start doing analytics with it there.
Thanks, everybody.